What if a wormhole appeared in the ground or sky, and Earth was confronted with a bizarre interdimensional apocalypse scenario? We may be in serious trouble unless the government has a group of superhumans hidden away in a bunker in the desert. How would we handle possible upside-down risks? The 27-kilometer Massive Hadron Collider at CERN smashes together elemental particles with such power that they rip one another apart as they are whipped about at extremely high speeds. Particle accelerators like the LHC enable us to discover new types of matter. They assist us in understanding the operation of quantum realm. But might they also tear our universe apart? The Large Hadron Collider is a modern marvel and the world's largest scientific instrument. It's assisting us in understanding what's going on with the matter we've made of, and how it behaves at the smallest scales and the most energized states. But does using it endanger our survival? Martin Rees, a British astrophysicist, has warned that large particle accelerators like the one at CERN could potentially create some bizarre apocalyptic scenarios. If something went wrong with the Large Hadron Collider or similar technologies, our way of life would end in three ways. The first concern for Rees is that these massive particle accelerators could produce strangelets. Strangelets are hypothetical particles that, if they collide with the matter on our planet, have the potential to condense it to the size of a soccer field. How would this work in practice? First, we must comprehend the composition of matter. All atoms are made of quarks, and we know the 6 types of quarks: the up quark, down quark, charm quark, top quark, bottom quark, and strange quark. Only the up and down quarks have masses that make up matter as we know it on Earth. The rest degrade quickly into other things. However, in the 1970s, physicists were curious about what would happen if atoms were subjected to super extreme pressure and energies. Atoms were pressurized to the point where their protons and neutrons split into quarks and their models. Under even greater pressure, the up and down quarks may condense, and some may become stable, heavier strange quarks. Once stability is achieved, strange matter appears. This matter could spread as strangelets or strange matter fragments. If this occurs, strangelets will spread throughout the universe like a virus. All other matter these viral particles come into contact with will be drawn to the stability and massive strangelets and instantly convert to a highly compressed state. This means that if a strangelet collided with the Earth, it would shrink to the size of an asteroid. When a strangelet hits the Sun, it condenses into a strange star and causes the Earth to freeze. Strangelets would float through the universe, transforming everything they came into contact with into strange matter. Stranger Things would be a literal episode of our universe. Should we be concerned that the experiments at the Large Hadron Collider will result in an upside-down universe of strange matter? Don't worry, say the people at CERN. The Large Hadron Collider must be more powerful to generate the environments required for quarks to morph into strange, stable matter. According to one report, it was about as likely as making an ice cube in a furnace. If strangelets and strange matter are physically possible, neutron stars are the most likely source. Aside from black holes, neutron stars are the densest objects in the universe. The pressure within these stars is so intense that it has the potential to rip apart atoms and transform up and down quarks into strange quarks. The strange matter created would eventually consume the neutron star, transforming it into a strange star. On the other hand, a strange star would continue to be strange, floating around by itself and having no effect on anything else. If two strange stars collided, they would release strangelets into the universe and speed through space, finding anything they touch. The second theory indicates that a large particle accelerator could create a massive black hole, sucking up our planet and possibly the entire solar system. We don't know about black holes, but physicists believe they form when enough mass and energy are condensed into a small enough space. The black holes we've seen in our universe form when massive stars died at the end of their lives. There's a chance that when tiny particles collide, as in CERN's Large Hadron Collider, they'll create little, tiny black holes rather than a huge Earth-eating one. According to physicists' theories, this would be possible if there were more than 3 dimensions. According to intricate mathematical models built on string theories, these tiny black holes could form in 6 or even 10 dimensions, at specific super-high energies. String theory proposes the existence of gravitons, or hypothetical force carriers for gravity, hurled into tiny loops within the space we already know exists. Currently, gravity is not included in the standard model of particle physics, and calculations and observations at the microscale do not account for its force. The discovery of gravitons may aid in bridging the gap between the standard model and the quantum realm. These particles, like photons and bosons, are not single-point particles, but rather little ribbons of energy or strings that vibrate in various ways. The equations of string theory are dense but extremely elegant, and more importantly, remarkably consistent. These ribbons have curled into tiny balls less than 10 to the power of negative 33 centimeters wide. However, the strings in these tiny coils of interdimensional space are far too small to be measured by a Large Hadron Collider. 10 million billion times smaller than anything detectable by the particle accelerator. So, should we be worried if tiny black holes are being torn through interdimensional space as particles crash into each other? Well, probably not. The Earth is bombarded daily by particles that collide with the atmosphere at energies more than 100 million times greater than what can be produced at Large Hadron Collider. These little guys may already be around us, but we haven't been able to observe them. If they are, they haven't yet engulfed our planet. Furthermore, these tiny black holes would be extremely unstable. If they did exist, they wouldn't only exist for a fraction of a second. In their three-dimensional world, their decay time would be 10 to the power of negative 83 seconds. The shortest time we can use for physics to have any meaning or use to us is about 10 to the power of negative 43 seconds. Space-time itself may be torn apart by all those particles collisions at CERN poses a third potential issue. Rees claims that the void of space, which we typically consider empty, may be quite fragile and contains more material than we realize. Theoretically, by causing a phase transition, a strong enough particle accelerator could rip space apart. Phase changes happen frequently. They happen whenever water condenses to form steam or ice. They happen when atoms lose an electron or become ionized. These changes occur often. However, the notion that a machine created by humans could tear the cosmos apart has been thoroughly disproved. There are forces at play that are beyond our capacity to recreate them. At energies that we could never hope to reach by building an apparatus like a large particle accelerator, phenomena like supermassive black holes, quasars, that shine brighter than entire galaxies and others take place. At least not at the scales they are currently built for. We might not need to be as concerned about particle accelerators destroying the universe as we know it. We might run into issues if we built one across the entire diameter of the Sun or the Earth in the future. It's also significant to remember that Martin Rees has been quoted as saying that these doomsday scenarios are unlikely to occur. The Large Hadron Collider's primary function right now is the discovery of new particles. It assists in our understanding of the quantum world and helps us recreate the creation of the universe itself. It might shed light on the nature of dark matter and the existence of extra observable dimensions. After a few years of inactivity, it has been operating for a few months. It was modified and enhanced during that time. Physicists at CERN have already found 3 new particles since it resumed operation. Technically, they are combinations of existing particles known as pentaquarks and tetraquarks. Usually, we are aware that matter is composed of 3 quarks combined. For instance, the proton has 2 up quarks and 1 down quark. Still, recently researchers have discovered penta and tetraquark particles with 4 and 5 quark configurations, thanks to particle accelerators. According to researchers, 3 new types of these particles were discovered after the Large Hadron Collider's most recent run. They are rarely found and are frequently referred to as exotic particles. They appear and disappear in a fraction of a billionth of a second. But their brief stay in space and time may be able to shed light on the events that took place at the very beginning of the Big Bang. Scientists can start compiling a periodic table for exotic particles as more and more of these phenomena are observed, which will help them better understand the incredibly, extremely small forces that influence the very fabric of existence. The Large Hadron Collider therefore might not bring an end to the universe as we know it, but it might enable us to understand how it came to be. That is our video for today. We hope you like it. Do you think the work being done at CERN is safe? Share all of your thoughts with us in the comment section below. Well, that's all for now. This is Big Tech Media. See you again tomorrow. Keep in mind to like, share, and subscribe.